You've got Prometheus collecting all of this metric data, and we can make sense of all that data by making queries to it using the Prometheus query language PromQL. In this lesson, you're going to master PromQL. You're going to start from very simple metric queries and build your way up to production-grade monitoring. So let's not waste any time and dive right into it. Chapter 1, we're going to get started. It's going to be a very quick chapter because I already have Prometheus set up and scraping metrics from a Python application. If you want to have the same environment as me to practice for this lesson, go to this video, the link is inside the description, and then come back. If you already have Prometheus collecting your own metrics, that's perfect because all the queries we're going to write in this tutorial will work with your data as well. And so it only makes sense that in chapter 2, we seek to understand all of the different metric types before we perform any queries on them. Okay, so at this endpoint, I've got a Python application that is exposing many metrics. And in the back end, Prometheus is scraping all of these metrics every 20 seconds. And ahead of each metric, there are two comments. A help comment that describes what the metric is, and a type comment that defines the type of metric that we're dealing with. Okay, the three most common types of metrics that you'll ever encounter are counter metrics, gauge metrics, and histogram metrics. We'll start by discussing the counter metric because it's used for measurements that can only ever go up. One such measurement is the total number of HTTP requests made on a particular path. So here we're tracking the total requests made on the path/metrics. So far we've got 3, but if I refresh the page, it should increase because Prometheus behind the scenes is actively making requests at this path in order to scrape all of this metric data. Okay, but let's look at some more interesting output. What if I make a request to the application's homepage at localhost 8000? I'm going to make 4 more requests, so 2, 3, 4, 5, refresh the metrics page, and now I see over here that 5 requests were made on the path /. And so that's the thing with labels, they add dimensionality to your data. For the same metric, we have 2 different measurements, one that tracks the total number of requests made on the path/metrics, and one that tracks the total number of requests made on the path/. The second metric type that is very common is the gauge metric, and a gauge metric is one that goes up and down very frequently. One such metric that is most common is the CPU usage, because CPU usage, as you all know, goes up and down depending on the amount of workload, depending on the amount of traffic that the application needs to handle. Okay? And the third type of metric that is very common is the histogram metric. A histogram metric is ideal for measuring request duration because it's a metric that just needs to be distributed into many buckets. Why? Well, if I just told you that most requests made on the path / took 5 milliseconds on average, that doesn't really tell me much. What I want instead is a distribution that tells me how many requests took less than 5 milliseconds, how many requests took less than 10 milliseconds, so on and so forth. Okay? So here, out of all 5 requests that I made on the path /, 3 requests took less than 5 milliseconds. The bins are cumulative. 1 more request took less than 10 milliseconds. And here, 1 more request took less than 25 milliseconds. And because the bins are cumulative, I can ignore the rest. So now here I can say that most requests fall inside of this bucket. Most requests are taking less than 5 milliseconds, which means my application is pretty healthy and processing requests very quickly. All right, so that's all for the different metric types. All of this metric data is being regularly scraped by Prometheus every 20 seconds and saved into the Prometheus database. I can access the data being saved into the Prometheus database through the Prometheus UI, which, based on my setup, is in localhost 9090. If you have the same setup as me, feel free to go there because we're going to be querying the data inside of the Prometheus database. And because we know all of these metrics are in Prometheus, the simplest type of query we can make is just by pasting in the metric itself. And if we execute this query, what that's going to do is display all of the metrics, all of the measurements that match HTTP request total. Here we see the number of requests made on the path slash, and here we see the number of requests made on the path slash metrics. Okay. And now what I'm going to do is something called label selection, essentially filtering our output to only include the metrics that match the labels we're filtering by. I'm just going to filter our output to only include metrics that have the label path slash. Okay? And there you go. And now, in the interest of introducing more variety into our metric data, what I'm going to do, if you have the same setup as me, feel free to do what I'm about to do. If you don't, no worries, just follow along. You should have a collection.json file inside of your workspace. What I want you to do, if you have the same setup as me, is open Postman or download it from the web if you need to, and then import this JSON collection into it. What that's going to allow you to do is make requests to your Python web application. We can make requests at the root path. We'll make 2 more requests. That should take us to 7. Let me make sure. All right. We'll make, let's say 4 post requests. 1 get request on the path slash items slash 1. We'll make 3 get requests. Why not? We'll make some put requests. We'll make 1 delete request. And that's good enough. Let's refresh what we've got. So now we've got a variety of metrics being exposed by our Python web application. I'm going to wait a little bit to allow Prometheus the chance to scrape this data and save it into its database. It should have saved it by now. So now what I'm going to do, I'll start by removing the filter. Okay, here we see all measurements that match this metric. And now what I can do is apply a filter that says only include the measurements that are actually get requests. So my label is going to be method equals get. And just note that labels are case sensitive. Okay, and now it only includes the measurements that have the following label. And I can even apply multiple filters and say only include metrics that have the label method get and the label path is equal to slash. Beautiful. All right. Now something else I wanted to show you was regex matching, which is something that you can do in PromQL. So here I've got all of these metrics. One is a put request that is made on the path slash item slash 1. One is a post request made on the path slash items. 1 a get request. And now what if I want to retrieve all of the metrics whose path starts with slash items? So what if I want to retrieve this measurement, this one, and this one as well? What I can do is the following. I'm going to say, grab me all the metrics, and here we have an option to use regex to match all paths that start with slash items. Then we'll put a dot followed by an asterisk. All right, if I execute the following query, we get all the measurements whose path starts with slash items. Okay, I can go even further and say, get all the ones that start with slash items slash 1. And now I expect this one to get filtered out. And indeed it does. So you can use regex matching. And now let me remove the 1. And what I'll do is an anti-regex, a negative regex that says, don't include any paths that start with slash items. And we get exactly that. Cool. Before we perform any more queries, it's really important to understand why Prometheus is known as a time series database. So if I go to the endpoint where my application is exposing data, here we see the most up-to-date value of each measurement, the most recent value. But behind the scenes, Prometheus has been scraping this data nonstop every 20 seconds. So while here we see the most recent value of each measurement, in Prometheus, each measurement would have its own time series, where each timestamp in the time series records its value at a specific point in time. If I perform a query without specifying a range, what that's going to do is return the most recent up-to-date value of each time series. The output is called an instant vector. If in my query I specify a range of 5 minutes, what that's going to do is return a range of 5 minutes for each time series. This is called a range vector. Let's have a look right now. So here we see an instant vector, where each value is the most recent one for each time series. Okay, if I specify a range of 5 minutes, then what we're going to see is a range vector that specifies what the value has been for the past 5 minutes. So in the past 5 minutes, I didn't make any requests to the path slash. It follows that it didn't change at any of the timestamps. But here, because Prometheus is scraping the data every 20 seconds, we see that it changes quite often. Every 20 or so seconds, Prometheus makes a request to the path slash metrics. So this is a range vector because we get a range for each time series, and this is an instant vector because it returns the most recent value of every matching time series. Simple as that. So I want to boil this down to two definitions. A range vector computes a range of values per time series, and an instant vector computes a single value per time series. Nothing more, nothing less. I want you to really internalize and understand these definitions as I go over to the Prometheus documentation and show you that there are many, many Prometheus functions, some of which can be applied on instant vectors, and other functions can be applied on range vectors. The function I'm looking for specifically is the rate function, which is a very, very common function that expects to receive a range vector. And what it does is on each range in the time series, it'll calculate a per second average rate of increase. Let me give you an example. If we feed the rate function a range vector where each range belongs to an HTTP request total measurement, then what it will do is for the time window of each range, it will calculate the average number of requests per second. That's what a rate is. It's the average number of something per second. In this case, we're dealing with requests. Okay, so if I go over here and I query the total number of requests made to the path slash and the total number of requests made to the path slash metrics, I haven't made any requests to this path in the past hour or so, but Prometheus consistently makes requests to the path slash metrics. We can verify this by viewing the data over the past 1 minute. Okay? So over the past 1 minute, the number of requests on this path didn't really change. And here we see each timestamp is a single point in time every 15 seconds, whereby Prometheus is making a single request to the slash metrics endpoint. So if a single request is being made to the slash metrics endpoint every 15 seconds, and the rate measures the number of requests per second within this window, I expect the average rate here to be 1 divided by 15, 0.06667, and I expect this one to return 0. Let's try it out. All right, and that's pretty much it for rates. Now, very commonly, people compare the rate function versus the irate function. Let me go to it right now. So the irate function is very similar to the rate function in that it expects to receive a range vector and it calculates the per second rate of increase in the time series, but it only does it on the last two data points. Okay, so while the rate function computes the average number of something per second over the entire time window, what irate does is it only looks at the last 2 points within that time window and it calculates the instant rate of increase between these 2 points. So in a scenario where the frequency of requests is consistent throughout the entire interval, we would see very similar results for rate and irate. But in a scenario where everything is going fine, but in the last two data points, there's like a sudden increase. While this anomaly would be averaged out using the rate function, irate would show this sudden spike, this sudden increase in traffic. Okay, now for HTTP requests, rate is usually very good, and we're going to stick to it. But there's something interesting I mentioned in that rate and irate can only be used with counters. So if I go over to rate, should only be used with counters and native histograms. What if I want to measure how fast my CPU is changing over time because CPU is a gauge metric and we can't use the rate function on it? Well, you technically can, you're just going to get really, really weird results if you decide to do so. Well, what we can do is look at the documentation and we'll find out that there is a delta function that also takes in a range vector. And for each time series, it will calculate the difference between the first and last value. And this one can only be used with gauges and native histograms, which means we can use it on a metric such as CPU usage, okay, or CPU temperature in this case. So let's actually just go ahead and use it right now. If I go over to my metrics over here, we see that there's one called process CPU usage. What I can do is get the process CPU usage over the last 5 minutes, if you will. And here I see timestamps every 15 seconds over the last 5 minutes that show me how CPU is increasing and decreasing over time. If I want to get the change in CPU between the first and the last value, what I can do is say delta, process CPU usage, and there you go. And we get a negative 0.21. So in the past 5 minutes, CPU has gone down by 0.21%. Now I'd like to talk about aggregation operators, sum, average, max, and min. All of these operators have one thing in common. They expect to receive an instant vector, and they'll aggregate every value in that instant vector into a single value. Let's look at an example. So I went ahead and populated my application with some data, right? And now here, this query, what it does is it produces an instant vector because it produces a single value per time series. What I can do is aggregate every value in this instant vector into a single sum. So the sum, this aggregation operator, is going to get this instant vector as an input and produce a single scalar value. I can get the average rate of all the requests all the same, aggregating all the values in the instant vector into a single average. I can get the maximum rate among all the values in the instant vector, and I can get the minimum rate among all the values in the instant vector, which of course is going to be 0. Okay? All right, now before I continue, what I want to do is go back and just try to create some metric data, okay? I'm going to send in some post requests. That keeps creating an item with an ID of 3. So we're going to keep getting an item with an ID of 3, okay? If you choose an item with another ID, different than the one your post request produced, you'll get an item not found. All right, I'm going to update the item with an ID of 3. Okay, we've created some data. Let's go back, rerun the rate function. Cool, we have a more varied amount of data for now. And now what I can do is something called grouping by a label. What this basically does is it aggregates the values in your instant vector depending on the label that they have, essentially producing another vector. Okay, so I can say sum by method. What this is essentially going to do is aggregate every single value that has the method delete, every single value that has the method get, post, and put. If we execute that, we get a vector with 4 values. Each is the result of aggregating all the values that had the method delete, the method get, the method post, and the method put. Because the output is a vector, we can go even further and aggregate all the results of this vector into a single scalar value, into a single sum. Okay, that's pretty much it. So sum by grouping by a label before aggregation produces a vector. And just summing, just using a basic aggregation operator, takes a vector and produces a scalar value. Simple as that. Now we move on to aggregation over time. So just like how simple aggregators take an instant vector and produce a scalar value, aggregation over time functions, they kind of go up a dimension wherein they take in a range vector and produce an instant vector as a result. The sum over time function, for example, takes an arrange vector and it calculates the sum of all values in that specified range for each time series, computing a single value per time series, an instant vector. The average over time function, same thing, takes an arrange vector and it calculates the average of all values in the specified range for each time series, producing a single value per time series, an instant vector. Okay, you've also got max over time, which calculates the maximum value in the specified range per time series. Min over time, that one kind of explains itself. Okay, so let's go ahead and look at an example. What I'm going to do is start by flooding the root path with some requests, just so we can see some data. Okay, and then I'm going to query the HTTP request total metric for the path equals /, and I want to look at the results in the past 1 minute. Let's make this 2 minutes. Okay, good enough. Now, if I do a sum over time, it's just going to sum the value at each timestamp. Okay, so that should be like 700 and something. Cool. If I do an average over time, it's going to get the average amount of requests in total in the past 2 minutes. That query makes a lot more sense than sum over time. Here we get 93 requests on average. If I do max over time, it'll get the maximum amount of requests in this time span, which is obviously 94. And the min over time, oh, we must have gone past the 2 minute mark. Now it's all 94. Let's do 3 minutes. If I do min over time now, we should get 90. Now, instead of just doing a single path, let's remove the label selector, and it calculates a minimum value in the specified range for each time series, producing an instant vector. If I do average over time, again, it originally took in a range vector. Let me just show you the range vector. It originally took in a range vector where each time series has a range of values, and it calculated the average of all values in the specified range for each time series, producing an instant vector. Pretty cool stuff. That's it for aggregation over time. All right, now we're ready to perform queries on histogram metrics. So here we have a histogram distribution for the request duration on the empty path, and this tells us that some number of requests took less than 5 milliseconds, some number of requests took less than 10 milliseconds, some number of requests took less than 25 milliseconds, so on and so forth. But just now looking at the raw data itself isn't very insightful from first glance. It would be very useful if there was some function in Prometheus where we could just give it all of the histogram data, as well as the percentile, where we can ask, hey, given this request duration distribution, how fast were 95% of my requests? How fast were 50% of my requests? And then it spits out a number. Well, that function is called histogram quantile, and we're going to look at it now. So if I go to my raw metric data, as it's being fed into Prometheus, we've got many histograms. The one we're going to focus on is the following, which measures the request duration made on the empty path / 17 requests took less than 5 milliseconds, 21 requests took less than 10 milliseconds, so on and so forth. So now what I want to do is output that same histogram onto my Prometheus UI using PromQL. So I'm only going to query the buckets that belong to the path /. Okay, let me fix that up. Classic label selection, press execute. Oh, my computer froze. There you go. So here we see the exact same thing. 17 requests took less than 5 milliseconds, 21 requests took less than 10, so on and so forth. Now, in order for this data to be fed into the histogram quantile function, the only label that it can have is the less than or equal to label. I have to somehow remove all of these. A workaround to this is to group each time series using the LE label. Because the LE label is distinct for each value over here, it follows that we're going to have the exact same number of groups as there are time series. So I'm going to wrap this up into brackets, group everything using the label LE. And because there's exactly one group for every time series, it doesn't really matter which aggregation operator we use. It could be sum by LE. It could be average by LE, min by LE, max by LE. You get the point. Let's just use sum. Okay. And now that we've got the buckets in this form, I can now feed it into the histogram quantile function. Histogram quantile. And now what I can tell the histogram quantile function is, hey, given this distribution of data, can you calculate how long 95% of my requests took? And this tells you that 95% of my requests took less than 22.7 milliseconds. Pretty darn cool if you ask me. Now what I'm going to do is go to Postman and make a lot of requests to the empty path. I'm going to make at least 10. Now 95% of requests took less than 16 milliseconds. I can change the percentile to 50. And this tells you that 50% of requests took less than 3 milliseconds. So I hope you can see how the histogram quantile function allows us to extract very valuable insight from our histogram distribution. In this chapter, you're going to learn how to compute meaningful averages and totals. A very common average to compute is the average number of seconds that a request takes to process. And the way to calculate this is to take the rate at which the duration of all requests is increasing per second and divide that by the rate at which the total number of requests is increasing per second, and that will yield the average number of seconds that each request takes. So here we've got many histograms, and after each histogram, there are two measurements. The first one is the total number of requests, and the second one is the total time spent on all requests. So here you can see we've got 36 requests that took less than 5 milliseconds, 41 requests that took less than 10 milliseconds. If you get the total time spent by all these requests, you would get this number right over here. And so if I want to get how long each request took on average, and the way to do that is first, let's grab the total time spent by all requests to process on the path slash, and let's view it as a range in the past 5 minutes, okay? So I haven't made any requests in a while, which means if I apply a rate function on this, I'm just gonna get 0 because the request duration hasn't really changed in the past 5 minutes. So let me go to Postman, make a lot of requests on the empty path. Okay. And let's bring this window down to 2 minutes. We'll give Prometheus a chance to scrape the metric data. It hasn't done so yet. So here we can see that things have changed. Has it changed in Prometheus yet? All right. So now what I'm going to do is take the rate at which the request duration has been increasing in the past 2 minutes and divide that by the rate at which the total number of requests made on this path has been increasing in the past 2 minutes. So we'll just copy this over. And this gives me the average time that it takes for each request to process on this path. Simple as that. And now let's talk about totals. A very common total to calculate is the total requests over time. And Prometheus provides a very handy function in order to do that. And that is a function known as the increase function. So the increase function expects a range vector should only be used with counters, and it calculates how much the value increased by. So going over here, let's choose HTTP request total metric on the path slash. Why not? What I'm going to do is make 10 requests to it now. So I'm going to send a lot of data. Maybe not 10, we'll see how much. And then what I'm going to do is say HTTP request total in the past 3 minutes. Specifically for the path slash, just to keep things intuitive. Okay, so the increase in requests within the 3-minute window at this timestamp is 66, and then now it's 77. So 77 minus 66 is 11. So if I calculate the increase in requests within the 3-minute window, am I going to get exactly 11? We'll find out. And we get 11.999. And the reason that we don't get exactly 11 is because it assumes that, hey, maybe this window isn't very big and it only caught part of the increase. So it tries to extrapolate to a fuller time range, which is why we don't get exactly 11. But the more you increase the window, the less that it has to extrapolate, and the smaller this value is going to get. The closer it's going to get to the increase that it originally calculated. Okay, so now we get 11.73. And that is how you can measure the total number of something and how it increased over time. Okay, now there are many functions. You really got to be careful to choose the ones that apply to counters and choose the ones that apply to gauges. So while increase measures how a counter value increases over time, the delta function is used to measure how a gauge value changes over time. And you really got to be careful to apply your functions on the correct metrics. Really look at the documentation. All right, and now let's look at how we can manipulate the existing labels of a metric. The first function we're going to look at is label replace. And what this does is it simply creates new labels from existing ones using regex patterns. And this is very useful, for example, if let's say you're making PromQL queries from Grafana and you want your panel to have an insightful label that doesn't already exist inside the metric, among many, many other use cases. So the metric we'll start by looking at is HTTP request total. Okay. It's got all these labels: instance, job, method, path, and status. And I just want to give it a new label called new label. Who cares for now, just for the sake of example. Label replace. So the first argument is the metric itself. The second argument is the new label, which I'm going to call new label to keep things intuitive. And the third argument is the replacement value, what to put in the new label. You could just put a standard string like hello world, but that wouldn't be very interesting. We want to put in what is commonly known as the first capturing group. I'll explain what that is in a second, but it essentially connects to the fifth argument, which we'll define in just a sec. The fourth argument is the label that we want to extract our value from, the source label. And the fifth argument is the matching pattern. So parentheses in regex, they define the capturing group, what's being captured. In this case, anything that comes after the slash, so it can match any single character that comes after the slash, and asterisks means there can be 0 or more characters after the slash, but essentially, anything that comes after the slash, we want it to replace this $1 as the value for our new label. Okay, so it follows that each metric is now going to have a new label that equals whatever comes after the slash. All right, pretty cool stuff. All right, and that's pretty much all I want to cover for label replace. It creates new labels from existing ones using regex patterns. Another function that we can use is label join, which combines multiple label values into one new label. And this is useful when you want to create combined labels for better grouping and filtering. So we'll go ahead and say label join. The first argument is the metric itself. I want to create a new label called instance info that combines the values of two other labels. In the third argument, we specify the character by which we're going to separate these two values. And in the fourth argument, I specify the value of the first label, followed by the value of the second label. So what this is ultimately going to produce is the value fast API app colon fast API app 8000 for instance info. Okay. This chapter is going to be very simple because I just want to touch on monitoring resource usage. So a metric you'll encounter very often is process CPU usage. This one just shows the current CPU usage percentage. In this case, 4.9%. Why is it inconsistent? Let me refresh. Oh, it's just a matter of Prometheus scraping the data at the right time. And another one you'll often encounter is process memory usage bytes. This is in bytes, but what I can do to convert it to megabytes is divide by 1024. That gives us kilobytes. Divide by 1024 again, and that gives us megabytes. Chapter 13 will be focused on visualizing data trends. For instance, what if I want to show the rate of change of memory usage in the past hour? If we look at the documentation, the rate function is used to calculate rates of increase for counters. But memory usage in this case is a gauge metric, and the equivalent of rate for gauge metrics is known as deriv. All right, this calculates the per second derivative and should only be used with gauges. And we're about to use it with a gauge metric called process resident memory bytes. So let's go ahead and do that right now. We'll just apply deriv, process resident memory bytes. Oh, we don't need the value itself. And process resident memory bytes. This means the memory actually used by the process in bytes. And we want to visualize the rate of change over some time span. I'm going to make that into an hour. Actually, before I show you the final output, what I want to do is just show you the metric itself in the past 5 minutes, if you will. Here we get a range vector with 2 time series, one for the Fast API app, the application whose metrics Prometheus is scraping, and one from Prometheus itself. Prometheus also keeps a metric for itself that keeps track of the amount of memory that it's using. And here we barely see a change for my Python app because Fast API apps, they typically have very, very stable memory. But Prometheus, it naturally grows as it collects more data. So we can expect a higher rate of change for that and a 0 rate of change for my Fast API app. Let me just stop talking and apply the function. Let's say over the last hour. So my Fast API app is essentially growing at 0 bytes per second and my Prometheus instance at 2 kilobytes per second for short. And now in this final chapter, we're going to explore some advanced functions. Although they're labeled as advanced functions, I find them to be very, very intuitive. So let's assume we have the metric HTTP request total, and I want to retrieve the top 5 time series with the highest number of requests. So what I can do is say topk, get the top 5. So the first argument is how many results you want to display on which instant vector. We get 4, 20, 22, 94, 21, 6, and 5. The rate function also produces an instant vector of, in this case, requests per second for each time series. And I can rank them by the highest requests per second to lowest. All right, simple as that. We just recently made requests here. That's why we're seeing actual values for it. Metrics requests are always being made there. Here we haven't touched those in a while. And just like there's top K, there's also bottom K, but then this one gets the bottom 5 values, which have the lowest request rates in this case. So you're just going to get 0 all around. And that's pretty much it for this PromQL guide. This tutorial covers almost every major topic. So if there were some topics that you weren't sure about, go back, take some notes. Trust me, I wish I had a tutorial like this when I was getting started because the Prometheus documentation is very interesting to say the least. In future videos, we're going to perform PromQL queries in order to construct Grafana visualizations, so make sure to tune in for that. And finally, if you haven't signed up for my Kubernetes course yet, what are you doing? Link is inside the description. I'll see you in there.